As promised, Newton's law of cooling states that the rate of change in temperature of an object is directly proportional to the difference between its current temperature and the temperature of the room. And that should make sense if you think about it. I hope. But let's turn that sentence into an equation. The rate of change of the temperature of an object. So the rate of change of the temperature with respect to time, dt, is directly proportional to a difference. Okay, the difference between the current temperature, which is not constant because it's cooling or perhaps warming, depending. The difference between that and the temperature of the room. And our temperature of our room is 75 degrees. For these problems, it becomes very convenient to assume that the temperature of the room is constant. If it's not, then we would have to put some sort of function in there, and that becomes very confusing. But the question might become, should we put t minus 75 or 75 minus t? It turns out it doesn't matter. That'll just change the value of k, whether k is positive or negative. But think about a very big difference between the temperature of our object and the temperature of the room. If we put a 200-degree piece of metal in your room, it's going to cool down pretty quickly because the 75-degree ambient temperature is so cold that it's going to suck the heat out of that object really, really quickly. If I put just an 80-degree hunk of metal in the room, it's not going to cool all that quickly because the difference is not so great, right? So the bigger the difference is between the object's temperature and the room temperature, the bigger that difference, the faster the temperature is going to change. All right. Okay, so when we solve this differential equation, you have to get the cat off of my lap. Hold on. Kitties love calculus. That's what they say. Anyway, we've got a separable differential equation. We'll divide both sides by t, big T, minus 75. We'll multiply both sides of the equation by d little t, and we'll integrate. Okay, and just like before, we can see that we're going to get that natural log of t minus 75. We don't need the negative this time because I put the variable first and the constant second. That's going to equal k times t plus c. We exponentiate, we get t minus 75 equals e to the kt plus c, which, as we've seen several times now, is the same thing as some other c times e raised to the kt. And then we can solve for big T by adding 75 to both sides. So 75 plus c e to the kt. All right, so we have two different initial values that we can use to solve for c and k. Always start with t equals 0. We love t equals 0 because that makes things so much nicer. At t equals 0, we get a temperature of 190 degrees is equal to 75 plus c times e to the 0, which is just 1. Subtracting 75 from both sides gives us 115 equals c. All right, so now we have 115 here for c. Now we're going to use t equals the other value they give us, which is, where is it, 5. 5 minutes, and that is going to give us a temperature of, well, 20 degrees cooler. So instead of 190, we're going to use 170. So 170 equals 75 plus 115 e to the kt, but t is 5, so 5k. All right, so subtract 75 from both sides, divide by 115, and we get 95 over 115 equals e to the 5k. Take the natural log of both sides, divide both sides by 5, and we get our K value. So our big T value, our temperature as a function of time, is going to equal 75 plus our C value of 115 times E raised to the KT. So I'll do 1/5 natural log of 95 over 115 times T. And if you feel like it, I always like to do this. It always kind of makes me a little happy to rewrite this. You can do the little switcheroo, and we'll have 95 over 115 raised to the T fifths. Again, that's the same trick I've shown you a few times. If you want to reduce the 95 over 115, that's great. If you don't want to, that's great too. We're going to be using a calculator, so the calculator doesn't care whether our numbers are reduced or not. But I definitely feel like this is an easier thing to type into the calculator than the previous line. So again, it's a matter of preference, but whatever makes it easier for you is what you should do. All right, so there's the equation we're going to be using, and the next question is, can we find the temperature of the tea at 10 minutes? So it cooled 20 degrees in the first 5 minutes. I wonder if it's going to cool another 20 degrees in the second 5 minutes. Try to answer that question yourself. Is it going to be a cooling of 20 degrees again, or is it going to be more than 20 degrees, or is it going to be less than 20 degrees? If you understand the premise, you should know the answer already. All right, so at T equals 10, our temperature is equal to 75 plus 115 times 95 over 115 raised to the T over 5. Whoops, raised to the 10 over 5. Forgot that we know what little t is. And that looks like a job for a calculator, which informs me that the temperature is approximately 153.478 degrees Fahrenheit. Notice that I'm always rounding to 3 decimal places. That's kind of the general rule in this class. The College Board, for whatever reason, likes 3 decimal places. And if we think about this, we notice that it cooled less than 20 degrees during the second 5 minutes. It went from 190 to 170, and then it went from 170 to 153. So perhaps that's not surprising. I hope that's not surprising. Our temperature is closer to room temperature now, so the rate of change is going to be slower. The cooling is going to slow asymptotically towards the room temperature. Alrighty, cool. So that is, I guess, the forwards direction that we could ask. The backwards direction is asking the question, when will the T reach 150 degrees? Okay, that's not going to be at T equals 10. It's going to be a little bit later, right? It's going to be at some future date. So this is when T equals 150. So we're going to say 150 equals 75 plus 115 times the fraction, 95 over 115, raised to the, we don't know what t is this time, so little t divided by 5. So we'll solve for little t. Subtract 75 from both sides and get 75. Divide both sides by 115. And that's going to equal 95 over 115 raised to the t over 5. Okay, so we'll take the natural log of both sides like we did on that other problem. And we'll get the natural log of 75 over 115 is equal to t over 5 times the natural log of 95 over 115. Again, just using the properties of logs, pull that exponent out front. Divide both sides by that crazy natural log, and then multiply both sides by 5. So we get 5 times the natural log of 75 over 115 divided by the natural log of 95 over 115. That would be the crazy exact answer for t. And again, turning to a calculator, we can find the approximate decimal value of t. And once again, Desmos to the rescue. Similar sort of problem here. And we can double check that graphically. Y equals 150 crosses the curve at 11.186. Notice that the exact expression's decimal evaluation is 11.186. That is the approximate amount of time in minutes it will take for our t to get down to 150 degrees, which is slightly more than 10 minutes, which we already knew was going to be slightly more than 10 minutes.